Hi everyone and welcome to today's session. So today we will be touching on something very fundamental. It's called embeddings. And embeddings has been around for like 30, 40 years. And it is basically what defines the meaning of a word or like a token in recent transformer terms.
This is about language and like how words. This is a very basic introductory lecture on how.
Yes. So basically in this embeddings, it is how we use it to define meaning. And I would say that how we define meaning is very critical for the performance of such a language model, because how you understand my words, it determines how you do your decision later on. If you do agents, it also determines how you assess what I'm saying, how you respond to me. And these embeddings, how to learn them properly is a huge challenge. I mean, we haven't learned them fully properly yet, but it is good enough to be versatile right now with the transformer embeddings. So today I'm going to take you a walkthrough of how embedding started. Okay, at least the first few things that I know of, from bag of words to the later more performant models of word2vec. And finally, we end off with transformers. And we'll go more into my latest research on context-dependent embeddings, which is quite exciting, by the way. Yeah, you will see how we can manipulate embeddings to suit your context. So without further ado, let's begin. So bag of words. All right, so what is bag of words? Bag of words is very, very simple idea that basically in order to evaluate the meaning of a sentence, we just simply count the words in it. So for example, this sentence, she loves pizza. Pizza is delicious. So you can count the number of times she appeared. So she appeared one time, pizza appeared two times, loves appeared one time. So you can see this embedding here, this sentence embedding here is basically the count of your words in that sentence. So like she is a good person, you can see that she is good. Yeah, so you can fit this later into some classifier systems, to see whether or not like maybe this sentence, is it spam? Is it not spam? So in the earlier days of spam detection, it is all using bag of words. And they just detect whether certain spam words occur. So bag of words, very rudimentary, but quite useful for earlier systems. Okay, however, it doesn't scale up that well. Okay, why? Okay, imagine if I type pizza wrongly, okay, and a pizza becomes P-I-Z-A. Or if let's say I have another word called pizzas, all right, this is actually going to be about the same meaning as pizza, all right, but it's not factored into account because each separate word is counted separately. All right, so another example is like the word walk, walking, walks, walks. Yeah, all this actually have similar meaning, but whenever you change the structure of how this word is, you kind of have to count a new word and you have to learn a new meaning for that word itself. Okay. Granted, some people have done stuff like stemming, where you just take only the root word, like you don't take in this part here. That's one technique that we can use. However, the issue of bag of words still remains, okay, is that you have these words. Whenever you change the words slightly, although the meaning is the same, you have to relearn the same thing again, right? That's one problem, right? Similar words not taken into account. Okay, the other more critical problem, all right, is this thing called word order. All right, so what is word order? So imagine like I have this sentence, okay? Like A is B's father or something like that. Imagine if I change the order, B is A's father. Okay, is the meaning of the meaning of the sentence the same? Anyone? If I rotate the order of the words, is the meaning of the sentence the same?
No.
Yep.
Okay, so the answer actually is more towards no. Okay, because if we actually change the order, like A is B's father and B is A's father, actually it means different things because the order is different. All right. So like for example, if let's say I have this, he is not satisfied. Okay, let's think of negation now. All right. So if let's say I have another sentence like this, like I am okay, let me think of how to do this negation. I am not happy and sad. Okay. Versus I am happy and not sad. Can you all see that the two sentences here have different meanings? Can you see that? All right, one is sad, all right, because not happy, and the other one is happy. Okay, so the way these negation words appear in the sentence where the word order is actually very critical for the meanings of the words of the overall sentence itself. And unfortunately, back of words, the usefulness stops there. Okay, it can tell you the composition of words in the sentence itself, but it cannot really tell you whether the sentence is like a certain meaning, because the word order plays a part in deciphering the meaning. Okay, so how do we solve this problem? So maybe we could, have a better way of representing words, okay, that cater to solve the first problem of like similar words not taken into account. We could try to solve it by making it into continuous vectors, right? How to solve these negative meanings? We need to take into account sequence, and that will factor in a separate model as well. So first, we ask ourselves this question: can we do better than the earlier model of bag of words? Can we represent words instead of just distinct like binary yes or no, or like frequency counts of a certain word? Can we actually represent words by a continuous space, a fuzzy space, okay? So that we can group similar words together by their location in that space. Okay, a lot of people call this space latent space or abstraction space, but this is the idea of what I mean by space, all right? So imagine you have this word called man, all right? And you have this word called woman, all right? And you have king and queen in another part of this space. Okay, because the idea of king and queen is one is male, one is female, is it possible to, just subtract away man from king and we get this word here? So if king subtract away man, I don't know what it means. It means royalty, maybe. Maybe the word here is royalty because it's gender agnostic. And then you can add back women and you get queen. All right, can you do such manipulation? Because if you could do something like that, it means that your word is very flexible. The representation of your word contains like the meaning of whatever constituent words that lead you there, right? That's a very powerful idea. And one of the earliest models that did something like that you can represent it in continuous vectors, is called word2vec. So this is the idea of word2vec. You can just do arithmetic for your vectors, and you can lead from one vector to another vector like that. Okay. So if let's say you have something else, like for example, instead of queen, you could have like the husband, the wife of the king. If you could have a chunk of tokens like that, okay, granted word2vec is not a model that can do this because word2vec does with words. What if you could do something like this, like you could have a sentence of wife of king and it comes to the same space as queen, all right? Then you could flexibly change your words, all right? So other ways of saying this is like women, or you have the word lady and lady appears somewhere here. So you know that like if you substitute lady for women, the sentence means about the same thing. All right, so if you could do something like that, your word representation would be very powerful. And this is even more powerful than the earlier model you saw. You know what's the earlier model? The earlier model is the bag of words model. If you could do something like have a representation for each word rather than a binary meaning like that, your representation is so powerful, you can swap words, you can substitute words, and you can do a lot of things. Because like if you know what words are similar to each other, you don't have to learn like a sentence with every single word. You can just sub in the word and you will still understand. Like if I swap women with lady, and most sentences would still sound the same. All right. So how do we learn this? So word2vec. Okay, word2vec is a very popular method before transformers, all right, to come up with word vectors such that, with vectors, you can represent these words in a more continuous space. And what exactly are vectors? So you just look at this thing here. This actually is just some math to say that, your word map to vector space. Let me just write it out here. Your word, okay, V is a word, okay, map to a vector space. And what is a vector space? A vector space is just a list of numbers. Like you can see here, this is a vector space. So there are 4 dimensions over here. And these dimensions could be predefined. Like if you really, really wanted to, you could say that, okay, maybe this is talking about animals or like living things. So like the higher the number, the more living it is, the higher the number, the more similar to animals it is. You could define your own vectors like that, okay? And then you could assign a score to each of them. Okay, that's one way of doing vectors. Okay, however, in the era of deep learning, we don't really identify what each dimension means. We let the data we let the data train this vector. So while we could do like each vector, we could label the vector ourselves and we classify it ourselves and we give it a value, it's not very efficient because you need to label everything yourself. Can we do better than that? Can we learn the embeddings? Can we learn this vector representation purely by data alone? All right. And the answer is yes. All right. So this is quite a substantial thing, this idea of unsupervised learning. You will see this in transformers as well. This means that we can learn without any human labeled data. And this is very, very powerful. Okay, how does word2vec do that? All right, let's take a look in the next slide. So the idea is like this. How a word meaning, what the meaning of a word is actually very influenced by its neighbors. So for example, like the man walked into a store. Okay, you can change to the women walked into a store. The person walked into a store. Okay, but the idea with this thing is that because of the words like walked into a store, you could kind of tell that this word here, in general, it actually means a human, likely a human. Okay, because of the way you say walked into a store, and the store is like a kind of a place where humans go to. All right, it's not really like robot walk into a store. You wouldn't expect this unless next time we have cyborgs and everything. So you can see that your word here, you can define this word by just like presence of the neighboring words alone. And that is the idea behind continuous back of words. Okay, so this is a bit of a continuous back of words has nothing to do with back of words actually. So I actually believe they called continuous back of words because they wanted to like follow up from back of words. But the idea of continuous back of words is really just saying that, okay, you have other words beside your main word you want to predict. Okay, so for example, in this case, we could have some words like maybe I am something. So this word could be I am a blue bird or something like that. Yeah. So you could have words like this. And the thing is, given I am something, I am blank blue bird, can you, based on your surrounding words, predict whether or not can you predict this word from your surrounding words? Okay, can anyone like think? Do you think it's possible if I give you like two words on the left and two words on the right? Can you predict the middle word? And anyone thinks you can? Or
As a
can
rule,
I have some
you
response?
often
Yeah.
can. If you can't pick the word, you can often get pretty close, right? Context is king.
Right. So this idea of continuous back of words quite powerful. Okay, because you can basically use the words beside you to learn what the word is in the middle. And you can see that this works for any text. So this is the key idea I want to highlight. Any text. Okay, you don't have no human labels needed. Okay, sorry. No human labels needed. Okay, this is a very, very important idea. I'd like to harp on this idea again. No human labels needed. Okay, this is the key reason why transformers work so well. So, because you don't have to label your data at all, you can learn from the entire world's worth of data, the entire internet. Word2vec can learn from the entire internet as well. Okay, if you look at this part here, like the text corpora, they even have like common crawl. Okay, common crawl is like the data scrape from the entire web. So because you are just predicting the next word, you don't need to, or predicting the center word in this case for continuous back of words, you don't need to label your ground truth label at all. You can just take from the text. You just blank out one word and then you can predict that word. This idea of unsupervised learning by predicting a missing word, it's very powerful. Okay, it's what powers the latest transformer models as well, like BERTs, they mask out certain tokens. Transformers in GPTs, they mask out the next token or they predict the next token. And all this don't have to have human labels at all. Okay, anything that uses human labels is a very slow learner because you need human effort to label it. And if you need human effort to label something, you can't get a very big data set. And in deep learning models, data is key, right? So the idea that you can learn without human labels by just predicting the middle word is a powerful idea. It's a very, very powerful idea. And that's why word2vec was so successful back then. Okay, but how do they actually do this prediction? So the main thing is you don't actually binarize your thing into like, say, this is token number 111, this is 121. You could do that, but the idea is behind every token, okay, or behind every word, okay, this is just the word level, you could have a vector representation of your word. So like, for example, I could be like 0.5, 0.5, 0.1, and M could be like 0, 0.2, and 0.7. So what exactly do these numbers mean? Okay, as I said earlier, you could say that, okay, this category is for like animals, and this one could be for living things and so on. But in general, we don't predefine these categories because it's not possible to predefine them if you want to learn from unlabeled data. So we let the data like find the best representation themselves. So in this case, how do we predict this word here? They just take all these vector embeddings here. Okay, and then it's a very rudimentary method. They just sum up the embeddings. And then from this sum up embeddings, maybe you just use basically a perceptron layer where basically you just take this sum of embeddings and you try to predict this next word itself based on the embedding. So this is a very, very crude way of doing it. Okay, can you all see why? All right, if you sum up the embeddings, okay, this is a key criticism I have of this. If you sum up embeddings, you lose meaning. All right, imagine if I have 3 different embeddings. Okay, let's say I have this sentence here, right? And this sentence here has in the embedding space, it looks like this. I have one word over here, this embedding space, one word over here, one word over here. Like one word could mean like male, one word could mean female, and the other word could mean like dinosaur. Okay, and if I sum up all these words together, what will I get? I'll get something in the middle, right? The meaning of this whole sentence would be all in the middle here if I sum them up like that. Okay, I mean, maybe I should have another dot so that it's truly in the middle. Maybe I have one more dot here, like another unrelated concept like sky. All right, so if I sum up all the embeddings like that, can you all see that the embedding I will get in the middle here, like this dot here, this is not representative of the sentence at all. All right, it doesn't capture the meaning of the diverse inputs. So this is a key criticism I have of continuous bag of words. You sum up your embeddings, and by the way, there are some people who are trying to sum up token embeddings in transformers. These methods don't really work. Okay, you shouldn't sum up your embeddings like that. No, that's not how you interpret the sentence. Okay, but because of that, word2vec is not exactly that performant. All right, I would say this is a key reason why. All right, so this idea of unsupervised learning, I'd like to reiterate again, very powerful. Okay, although their method of doing the word2vec is not completely right, it still works quite well because of unsupervised learning. Okay, so the other way of doing the embedding prediction, yeah, sorry, by the way, in order to learn these embeddings, what we do is, because we have the ground truth word, we can backpropagate the gradients and then we update the vectors. Okay, how this is done, I'm not going to cover in detail, but the idea is you learn from you learn from this word's label, and then you backpropagate. So that's what it is. Okay, so the other thing that was used to train word2vec is called the scapegram. And what is a scapegram? A scapegram is basically you take the middle word here, and then you predict the surrounding words. Okay, but I'm actually not a big fan of scapegram. Okay, you think about it. Okay, can you do it? Okay, let's say this is I. Okay, we use the same sentence as just now. I am a bluebird. Okay, anyone can tell me, given the word I give you the word can you predict I am bluebird? Who here can do that? Raise your hand if you can do that. Okay, who here thinks you cannot do that? I give you the center word. Can you predict the 2 left and 2 right? Who here thinks you cannot do that?
Yeah, that seems pretty unlikely. Let's be honest.
Correct. So again, this is a flaw in the word2vec algorithm. I don't think this is a right approach to learn at all, but it still works performant for the times. All right. So this is the idea of prediction. And again, we do the prediction of the probabilities of the surround. So this is the scapegram method. All right. From the center word, you try to predict like the word probabilities to the left and to the right. All right. And this is the idea behind word2vec. The key thing I want you all to take away from this is not how they train it. Okay, because honestly, there are some flaws in the training mechanism that I just identified. The main thing I want you all to take away is that this is a purely unsupervised. I'm going to emphasize this again, okay? Because this is the key to today's learning methods. Unsupervised learning method. It learns without human labels. Okay, I think I emphasized that enough, all right? So because of that, you can learn from huge amount of data. And although, your training method might be a little not that great, but, with enough data, you can compensate for it. So this is the key idea behind the word2vec. And how can we take this to the next level, right? How can we actually improve on word2vec's method of training so that we can learn a better representation of our vectors? Okay, so one way that GPT is using and what OpenAI doubled down on, they invested billions on, is this idea called next token prediction. And this is a very powerful idea. And next token prediction goes something like that. You can predict the words coming out of my, okay, can y'all predict this word? Okay, so the answer is actually mouth, all right? So there's a lot of things that could be this blank here. But because of this idea of context, you already know what is the context over here. So let me just elaborate this. So you have the context leading up to the word. You can make a more informed choice of the word itself. So can you all see that this is a huge improvement over word2vec? Word2vec, you only have the two words on the left, two words on the right, predict the middle word. Right now with next token prediction, I have every single word that I've uttered until now, and then I ask you to predict the next blank. So you have a lot more context to predict, and you are predicting the next token given the earlier words, which is actually more natural than, giving you the next two words. This is another sentence. So, most of the time when we do prediction, especially like how we learn in our brains as well, like you are not exactly given like that, right? In the natural world, are you given like two words on your left and two words on your right and predict the middle? Okay, no, we are a causal prediction model, okay? Causal prediction. We only predict the future. We don't know what will happen in the future. Yeah, unless any of you here have time traveled to the past, there's no way you will tell what's going on in the future. And so any future inputs, like future two words or this, it doesn't make sense. You should only have inputs up to your current point of time, and then you predict the next word or the next token in the transformer case. So this idea of next token prediction, it's very, very natural because this matches how our brain thinks as well. We are a predictive machine. We try to predict what's going on in the next time period. Next token prediction does exactly that. And that may be the key reason why transformers work so well, because they are doing a causal prediction model using next token prediction. Okay, and BERT is a bidirectional encoder representation by transformers, but they actually do something like that. The cap is on the mat, right? They actually mask like that. The mask is on the mat on mask mat. Yeah, so they mask out like tokens, 15% tokens, and then they try to predict, given this entire sentence, what is this mask here. So while it's great if you already have the whole sentence and so on, but if you are trying to do like a generative model, you're trying to generate stuff based on what you have seen before, it's very unnatural to do this kind of learning, because what you are interested in is like you are just interested in this, but you are trying to train the model on like, given the future inputs, what is the middle inputs. This is not going to happen all the time. So the causal prediction is not there. So I would say that last time I thought BERT was actually more powerful, but come to think about it right now, my viewpoint has changed. I actually think that predicting the next token here is actually more powerful than BERT because of the way that inputs in the real world come to us. You only have the left side. You don't have whatever's on the right side, which is you don't have the future inputs. So this kind of next token embedding is actually a very, very powerful idea. Okay, before I move on to the actual illustration of the transformer tokens, just want to pause here for a while if you all have any questions on this idea of predicting the next token. All good? Okay, let's move on. So how does the transformer learn its embeddings? So this is the key thing that's powering most of AI right now, all right? The AI revolution that's happening right now is actually based on this word transformer. Okay, quite aptly named because they kind of transform people's understanding of stuff. So what this does is that they use next token prediction to generate the embeddings of the tokens. And how this next token prediction is done, let's look at this diagram over here. So I took this diagram from memorizing transformers because it shows you like each token. And for example, the input token is like said the cat in the hat, all right? And then the next word is actually 2, or the next token is actually 2. How can I predict, okay, based on whatever you have put here, how can I predict what the next token is? So this is a challenge by itself, how to do this predictive model. And the kind of answer that we kind of want to see is that we want to have all the earlier tokens help to contribute to the shape the meaning of this last token here, which is this thing here. We want to see all the earlier tokens shape the meaning of this last token so that this last token is very informative and has the context of the entire sentence. So this square here is very important because this square theoretically can contain the meaning of the whole sentence. So we just keep doing this for every single token. We take all the tokens on the left side, and then we do some form of self-attention. Okay, the self-attention basically, the key idea of self-attention is that you try to make tokens that are more similar to one another go to the same place, the same meaning, right? Okay, why is this so? All right, so here I need to bring you this concept of polysemy. Okay, polysemy means that there are more than one meaning to a word, or like token, to a word token. And this happens for the famous example I'm going to use is called bank. Okay, what are the meanings of bank? Okay, anyone can tell me what meaning can the word bank have?
A river bank, a financial bank, a
Okay,
slang
yep.
for cash. Yeah.
Yeah, so there's a few meanings, but the most common meanings are like river bank, financial bank. Thanks, Richard. And so in this case, if you just have the word bank alone, you are not going to have much idea of like, okay, most commonly is financial bank, but you're not going to have much idea that like, okay, which word do I mean? Okay, so word2vec actually suffers from this. Okay, they don't really have this self-attention mechanism, and that they can't really correct the meaning of this embedding based on the context. But with transformers, you can. So suppose the word river appears in front here, and then you have the word bank at the back. So because of the way we group tokens that have the same meaning to each other closer to one another using self-attention, the word bank would have some idea of the word river inside it. So river could influence bank because river appeared at the start. It could influence the word bank to mean something closer to river bank. So if we look at the embeddings representation here, so initially bank could be here. And then like here is the embedding for river bank. And then the other one here is for more financial bank. So by the presence of the word river in the beginning, we actually inch bank closer to river. So the earlier context tokens influence embedding representations of later tokens. And this in some sense helped to solve the problem of polysemy because by letting the embeddings influence the later part, whatever appeared at the start could actually give a new meaning to the tokens at the back here using self-attention. And this is very powerful. Okay, so by doing this, you shape the embeddings to a more contextual one, which could help to do the next token prediction better. So this, you can think of word2vec on steroids. This is transformer, all right? This really takes in the essences of the unsupervised learning of word2vec because next token prediction is also unsupervised. You just learn from the entire world's data. And we add in a very, very powerful predictive mechanism here because you can do prediction based on context, right? This is huge, okay? This is huge. Your embedding representation for transformer is way better than word2vec because of that, all right? And the idea of next token prediction is that, if you take similar words into account, all right, you can actually reduce like a statistical distribution when predicting next token over here, which also could mean that like if let's say your next token, you predict like the next token as male or man or boy, you know, okay, maybe not boy, but maybe male, man, or this, you know, these two words could mean roughly the same thing. All right. And if because they are doing a probability-based prediction, you are trying to predict the next token based on your existing tokens in the front. So because of this probability distribution prediction, if let's say your statistical distribution is very, very close, like male, man appears like similar in this kind of situations, the embedding for male and man would be updated accordingly, you know, to be almost the same. All right. That is also okay. That's one way. If the final prediction probabilities are the same, that's one way. The other way is like if you have two sentences, the man took the spanner, or the male took the spanner. If you have words like this that appears like interchangeably in your context, what you will learn is that you will learn that this embedding and this embedding is the same, because by the time you propagate back to the earlier part here, you will learn that the embedding layer for male or man would be the same, because this sentence appears like statistically like in a similar manner. So this also means that if you want to train your transformer embeddings, your data is very important. Okay, if you have the data that represents the wrong kind of meaning in your words, you know, then it's going to learn the wrong things. Okay, but we have to treat most of internet data, like if you take the overall percentage, most of it should be quite representative of how language should be used. Okay, unless people do some poisoning of data and so on, which could happen now. If let's say we treat that the data online is representative of how language should be used, then these two sentences, like the man took the spanner or the male took the spanner, it should occur almost the same number of times, and so we can learn that man and male are similar, right? That's how the embeddings are trained, okay, using statistical distribution of the text. Okay, and this solves the problem that bag of words had. Okay, how do we group similar words together? You don't need to do anything explicit. You just train on your data, and if by statistics the data occurs, the words are interchangeable, you know, you will learn that both words are have similar meaning. All right. Okay, so yeah, I'm just gonna pause here. Any questions so far before I move on to the next few points? All good? Okay, yeah. So if you all could just give some feedback would be good, because I like to know whether like the points are conveyed.
Yeah, can you explain the window for the transformers? Is there a concept of a window, John?
Okay, you mean a window for the inputs, right?
Yes.
Just like the word2vec. You saw word2vec earlier. Sorry, wrong slide. Word2vec earlier, you have this window of size 2, right?
Correct. So
Okay,
is
so
there
for
a similar idea in transformers as well?
thanks for asking that. So for transformers, actually, there's no real window left and right, because as I said, we are talking about next token prediction models like GPT. We don't actually have the rightmost tokens. Like you don't predict. Okay, let me just erase everything. You don't predict based on this. Like you don't predict based on the tokens here, right? You only predict based on whatever tokens you have here. So it is more like probability, the word two, given that say the cat in the hat, right? So you don't have like a window per se that, okay, I only take the last 10 tokens and predict the next one. Although you could, I mean, you could do that. So what transformers do is they take whatever context window they have here. Okay, so I guess the window could be everything from the start all the way to the current token, and then you want to predict the next token. So I guess you could treat the context as your window. Yeah, but it's not a sliding window. It is just take the entire thing. Yeah, so I mean, of course, up to your token limit. So like, for example, if you're using 3.5 turbo, your context limit could be like 4K for the smaller model, 4K token context limit. So if let's say if you want to train on the world's corpus, okay, you kind of need to like maybe only put like 3.3999 tokens as your context, and then you predict like the 4,000 tokens. Yeah, you could do something like that, because or you treat your 4,000 tokens as your context, and then you predict the 4,001 token. Yeah, so that could be some limitation because of the amount of memory that we have for the transformer here. You have a limited context window. So I guess you could count that as your window. Yeah. Does that make sense? Okay. So I'm just going to move on. If you have anything, just put that in the chat, all right? So next, what is one of the key reasons why transformers do so well is this idea of tokens. Okay, so earlier, remember I was talking about how words, like walk, walks, walked, walking, all this could have a similar meaning. But it kind of wastes the time that we have because we have to learn a separate meaning for each word as they are all different. What if we could just, perhaps mix and match such that the words become more reusable in reusable building blocks? So why can't we do something like that? Walk as, sorry, the first one is just walk as, walk ed, walk ing. So you could have words like this. Okay, and this is actually known as subwords in the literature. What if we could do something like subwords so that we could split the word up into parts, and then based on each part here, you already know that this walk, okay, you already get the meaning for walk because like it appears many times. Okay, S, E, D, I, N, G. Can you see that this also appears many times because like other than walks, you also have like runs. Okay, you have run. Okay, so that one is a bit different. Okay, running. Yeah, so you have stuff like that. Okay, maybe I give something that doesn't have this like talk. Yeah, so you have talk, talk, talk. So you can see that if you go by statistical distribution, you could actually learn the meanings of this whatever you add on to the right. You can learn that S maybe is plural, ED is past tense, ING is a continuous verb, and so on. And then once you mix them up with a new noun here, all right, you could already get the meaning of that. All right, so if let's say I were to give the transformer a new word that it has never seen before, like for example, let's take a verb, like maybe the verb could be, or we just take a noun. Let's say we have a transformer, but we don't really have this word transformer. Okay, this is a new English word. So new English word. Okay, it will break most systems. Okay, but with the token embeddings, you can just take meaning of transformer and ed and get a new meaning. Okay, so how many of you here have used ChatGPT and realized that if you type your word wrongly, it can still understand you? Any one of you have this experience? Like if you do a spelling error,
I've totally exploited it constantly. I can't be bothered typing correctly for chatbots. They can figure it out.
Correct. So, behind the essences of this, they actually don't have a spelling correction mechanism for you. It's just that because although some parts of your, okay, let's say, for example, in your word, like, for example, embeddings, okay? If let's say I spell it wrongly, I spell it one letter less, all right? What this could be is because maybe the word embed is still there. So they can still sort of figure out like, okay, it means embeddings. So this is the power of like tokens rather than words. If you spell the words wrongly, you can still get the meaning. And in fact, sometimes if you spell embeddings as like that, okay, but if you put like token embeddings of a word, okay, can you see that in a system that is smart enough to determine context? Okay, this might be garbage. Okay, this might be garbage. But because of your other stuff like token embeddings of a word, then you can ask GPT like, what is misspelled? Yeah, my spelling is quite bad today. What is misspelled? Because of the way that it has the tokens earlier on, okay, it's able to use these tokens here and, form a sort of understanding of like this sentence talking about token embeddings, but the word embeddings is missing. So you can say that this is misspelled. So this is quite powerful. Okay, we did not teach it this capability. We did not teach the transformer this capability, but because of the way we represent the words as tokens, and these tokens are using statistics to like group out words into subparts. Yeah, I mean, if you're interested in it, the technique is called byte pair encoding. where they just take similar Unicode characters and then group them together, and they keep grouping until a certain vocabulary, a certain size is formed. So this byte pair encoding. But it can generate stuff like top S, top ED, top ING because of the statistical distribution of your text. So this works for any text. Okay, that's the power. You don't have to have a linguist to say that, oh, this is plural, this is past participle, this is an adjective. You don't have to have a linguist to do that. Just purely from the statistics of how your characters are, your letters are, you can already group these subwords already using byte pair encoding. Very powerful technique. Okay, this idea of chunking based on frequency. Yeah, I've a guest speaker last time, Shu Cheng. She was also doing this idea of chunking. This idea of chunking and deriving meaning from chunks could be the basis of how we learn as well. Like, you don't want to define meaning for every single letter, right? Like, you want to define meaning for something that is more common in the world. Like, if you only see something one time, okay, you may not want to define it. Okay, but you see it many times, maybe you want to get a new word for it also, and so on. So this idea of frequency-based meaning deriver, yeah, I think this is quite powerful. So this is the idea of tokens, and it enables you to do a lot of things like group unknown tokens together, correct the tokens if let's say you have the other context around it. Okay, and with the power of context-based prediction, it is very powerful. I actually like the transformer so much. Ever since the GPT came out, ChatGPT came out last year, my entire discussion session has been focused on transformers because this architecture has been quite powerful, right? So there's a lot of things that it got right, okay, over word2vec, and I'm just emphasizing some of the stuff that that it got right. And the last point is context dependency, and this is the key thing that I was talking about earlier. You can use the earlier context tokens to guide you in predicting the next token. Okay, any questions so far on this? This is, I think, one of the most important slides for today, because this is exactly how the predictive power of a transformer is. I would say the key reason why it works so well is the way we can get the embeddings and how we can manipulate the embeddings to make it suit different contexts.
Can I be difficult? I'm going to feel free to skip on this question. No, you're not a huge fan of vision transformers, but how does image, so what about a term, tokenization or embeddings relate to text style embeddings and for these?
Oh, you're talking about how the vision transformers embeddings relate to this kind of...
or other vision techniques, but how other kind, in terms of text media, this is, for me, a very clear description. That's great. But so what I'm curious about is in other media, can you talk us through some examples perhaps of how those embeddings are generated?
Yeah, sure. So as you know from my last few discussions, I'm not a fan of vision transformers, right? You're aware of that, right? So why I say I don't like vision transformers, I mean, one thing is they break the image up into, I kind of need a blank slide for this. Let me go and find a slide that has fewer words. Okay, let's use this slide. So for vision transformers, you take an image like that, right? Let's say this is a person. Okay, and then actually what they do is they do something like jigsaw puzzle. They just group this up into like 16 squares. And each square, they actually embed into a certain vector. So like, for example, this square could be embedded into a certain token with a certain vector like that. Okay, so why is this bad? Okay, one thing is, if only in one spatial scale we lose meaning, like if you cut the face off halfway, you lose meaning of the face and so on. So I mean, this could be solved with tokenization at different scales. You could do another token of like larger size like that, which is essentially the follow-up work to vision transformers. That I kind of agree. Okay, because if you do different patches of different scale, like our eyes, the retina also, like you might cut things off, but if you analyze things at a bigger scale, you will get back your global context. Okay, so this is how the embeddings are. Each patch will be converted to an embedding, and then you pass through like an MLP. Okay. So MLP is the multi-layer perceptron. You can just treat it as a set of like linear neurons to map from one space to the output space. And then over here, the output space will be, you predict the class of the image. Okay, so this is the key problem with vision, all right? The key problem with vision is this. For vision transformers, they are trained using supervised learning. So I need to emphasize this, okay? Vision transformers are trained using supervised learning. Okay, why is this bad? It means that you are limited to what labels you have in order to learn.
Expensive and slow and unreliable.
Yes, correct. The reason why vision transformers could beat CNN, okay, is because Google, in their JFT 300 dataset, they use like 1,000 times the size of ImageNet. Okay, I don't know how big it is. It's huge. It's humongous. And a very inefficient method with a huge amount of data, you could and then they zero shot 99% on ImageNet, which kind of means that, maybe ImageNet is already in the training set. So I don't know. I'm not a fan of vision transformers. I think it's in the wrong direction actually. We shouldn't be doing supervised learning prediction. Okay, we shouldn't be doing that because like if let's say you are doing 1,000, let's say your class of image is 1,000 classes of image, like for example dog, cat. What if let's say I have a new class called dog cat. You don't know what okay, or cat dog. Okay, you don't okay, let's say we have this new class. You don't know what is that class because supervised learning, the class that you are predicting is not a continuous vector. It's just a binary like 0, 1. Yeah.
Are there any currently unsupervised learning strategies for vision?
Currently, the unsupervised learning doesn't work too well. Okay, let me explain why. Okay,
Sure.
some people have tried to do this, and they have tried to give okay, some people, I mean Meta, right? In the iJapa architecture. So, I mean, I'm a big fan of Yan LeCun, but I'm not a big fan of iJapa. Yeah, let me explain why. So, I mean, if Yan LeCun is watching this next time, I hope they can take this suggestion also. So, if this is the data that you are giving it. Let's say you're giving it this amount of squares, and then you try to predict this square. So one idea of unsupervised learning is that you split image into patches. I use a different color. You split the image into different patches. Sorry. Split image into different patches. Okay, predict one patch or predict some patches. So I mean, maybe you could do unsupervised learning like that. You could try to predict a patch. And iJapa tries to do it in latent space. You try to predict the latent space of that patch. Okay, but the problem is like this. Okay, in images, okay, let's say if I cover your eyes, okay, let's say this is a scene, all right. In image, if I have a scene like that, okay, and I have a person, then a person is walking with someone here. You don't know what this person is. If I just block off this part here, what's the chance of you predicting back this patch? Okay, so the idea is image is a high dimension domain. Like image is high dimensional. You have RGB, you even have transparency, There's like 255 times 255 times 255, okay, times whatever number for transparency, maybe it's 255 again. So it's like huge, okay? Like tokens, you maybe have word tokens. Maybe you only have like maybe up to 100K. For image, if let's say you want to do image pixel prediction, easily trillions or even more than that, because the amount of pixels are huge. Okay, so that's why iJapa, they try to predict in latent space, which is a bit smaller. Okay, but in latent space, you how I put it, yeah, it's not exactly easy to predict as well in latent space because of the huge amount of possibilities for the pixel space here. You see, this one could be a boy, this one could be a girl, this one could be a cat, it could be a dog. How are you going to predict just one latent space when there's so many possibilities for this image here? Okay, so in words, you could do that because like if you treat this as a word, like the man walked with the then here you have boy, cat, girl, dog. So you have many things that could happen in terms of like in this in the statistics for this, we could learn the statistics just like that. So if you can treat this like patch here as a kind of isolated technique here, yeah, then I would say it might work. Okay, but the problem is, it's not so clear cut. When you take away one patch of an image, it may not be a very clear cut word or clear cut concept. It may be many things that it's trying to convey. So when you're trying to predict this patch, you're not just predicting cat, dog, or this. You might also be predicting the background image because like there could be a pavement and then you want to continue the line of the pavement and so on. Yeah. So I would say that image prediction is a tough thing. Okay, we haven't solved it yet, and I think we will take about 5-6 more years to solve it. But once we solve unsupervised learning for images, we would hit AGI very quickly. Okay, right now we are just not able to do this because the way where we do prediction, even you take the patcher and you go into latent space, is still very complex. Okay, what I think we need to do is we kind of need to do some form of from vision, we kind of need to do some form of analysis of that vision first. So like analysis could be in different abstraction spaces. So maybe one space is predicting pixels, one space is objects, and then one space is maybe scene, like context. You could have different abstraction spaces and you try to predict each of them differently. So rather than predicting pixels here, like in this arbitrary chunk, we could, if we know how the objects are, like maybe how we get this object detection model, it could be supervised learning. It could be inbuilt heuristics, and like segment anything model by Meta. They can segment out different things by supervised learning. Yeah, so we could learn this. We segment out this object and then we do a prediction later on. So the prediction path for images is not so clear cut. I think it needs to go into separate systems and the prediction needs to be done there rather than on the baseline object itself. Okay, I went into a bit of a rant. All right, so I hope this is still understandable, but I totally think that we haven't solved vision yet for embeddings.
Fair enough, but thank you for my diversion into other media. Very helpful, thank you.
The rest, are you okay? This is not planned for, but I think this is interesting because I do have a big gripe about how we handle images right now. Okay, let's move on then. All right. So the idea of transformer embeddings, okay, is a simpler way as compared to images, as you saw just now. The idea of transformer embeddings is that you could use your context to predict the next token. That is very, very powerful to derive meaning in an unsupervised way. Okay, I need to emphasize this again. Unsupervised. Okay, we should really be doing everything in this way if possible, because you can learn meaning without giving human labels, and that's very, very important. And the idea of context-dependent learning using attention, also very powerful. So I mean, if I were to summarize transformer, is unsupervised learning, embeddings in continuous space, okay, and then context-dependent learning. So I think these are the three reasons why transformers are so powerful. Okay. Granted, there's one issue of transformers. Okay. Remember I said earlier that we have this issue in bag of words that we don't have the order of the words factored in. Anyone can tell me how does transformer factor in the word order? Anyone? If you all are familiar with transformers, what do they use? Attention is the way to learn the embeddings. But how do they factor in the word position or the token position in transformers? I give you a hint, it's also an embedding. It's just a different embedding. So okay, so I take it that y'all don't really know this, but it's okay. The thing is called the position embeddings. So with each token of the transformer here, like you give it a position 0, position 1, position 2, and so on. And these positions will be embedded into a vector as well. And then this vector would be summed into so the position vector is summed with the word token vector. Okay, so let me give you my graph on this. Okay, I'm not happy with this. Okay, so if you sum up the position vector with the word vector, okay, what happens is that you may lose the meaning of the word. Okay, so this is not a good way to do it. It's a workaround actually. Yeah, so I would say that we still haven't really found a system whereby maybe you could treat the position embeddings as a separate vector. I mean, I'll be more interested if, let's say, we could do this. We could do a position vector here, and then we could do the word vector here. We could concatenate the vectors like that. Maybe it would be better because then your position and the word won't interfere. Yeah, so maybe if we could do something like that, that would be useful. Okay, although this will increase the memory needed because you need to do two different vectors like that. Okay, so this is the key thing that I would like to say. The thing when you do into vectors, right, in transformers, actually they do a hack for the position. Okay, it's not the true idea of where the token is. So this is something that can be improved on, the positional embeddings for transformers, because like how exactly this is not really stated well. I mean, if you do some experiments with the embeddings, you realize that, you know, if you swap the word order a bit, you know, sometimes they might embed to the same thing, right? So this is not a foolproof way, okay, but it works quite well for now. So let's just take it. All right, any questions so far for this? Okay, if not, let's talk about more things with regards to the current context of retrieval augmented generation. All right. So in order to, you know, tell us like whether two sentences are the same or not, we actually use this thing called cosine similarity. And so cosine similarity, what it does is that, let's say we take the magnitude, this is the vector for an orange and this is a vector for the apple. Now, how do we tell whether both are similar? So maybe the orange has the embeddings like that, and I'm not sure whether this, I think that's an orange, and the apple has an embedding like that. So let's say we have this orange and apple like that. How do we tell whether both are similar? Okay, so what we do is we can do this thing called cosine similarity, which is this complicated math equation here. But you know, if let's say we take the magnitude of embeddings as 1, which is what OpenAI embeddings are. Okay, if we take the magnitude as 1, you can see that this is magnitude 1 and this is magnitude 1. If we do a cosine similarity, which is sort of a dot product like that, it's actually the angle here. It's in the math terms, it's just the angle between two vectors. So what this means is that in the embedding space, okay, we just assume that vectors that point towards the same direction are more similar. So if the orange vector is here, the apple vector is here, you know, both of them might be fruits. Then if let's say a dog vector is somewhere else, then it's a dog can be here. Yeah, dog can be here. Okay, so inherently this can actually cause some problems. Okay, because assuming all magnitudes are 1 and we differentiate the meaning of the vector by the angle. Okay, let's say I already filled up, let's say I have a 2D paper. Okay, I fill up apple, orange, and dog here. Okay, so maybe we could have a category like in the embedding space. Okay, we could have fruits over here, this category, and then we could have like dogs at this category here. Now I give you an object. I give you a paper, or maybe a printer. Okay, you know that your embedding space right now have dogs on the left and fruits on the right. Anyone can tell me where will you place printer? Where would printer go inside in this embedding space? Anyone? Like if let's say your left side is dogs and the right side you classify as fruits, where will you place printer? Okay, so the idea is that you don't have any more embeddings, any more dimensions left here. Your printer might be placed like somewhere in the center here. It's not very informative. So what will happen is we will need to expand out. We will need to expand out the embeddings. Okay, we need to expand this out. Sorry, eraser. We need to expand this out like that in a third dimension. And then your printer could fall over here. Okay, so I'd like to highlight this thing right now. Dimensions are important. Okay, more dimensions allow for more expressivity for your embeddings. And this is super important because if you have too few dimensions, what will happen is that your vector embedding is not as expressive. You will tend to group similar things together. Okay, you will tend to group even non-similar things together. Like for example, if your vector is not expressive enough, maybe your printer would fall inside this category as well, which is not what we want. Okay, so it's very important when you do embeddings to have enough dimensions to represent the amount of diversity you have in your data. So how many dimensions is good? Okay, we can discuss that in the discussion. All right, but the idea is not too little. Okay, but too many dimensions, is it bad? All right, so that one food for thought. All right, you can think about it. How many dimensions should we have for the embeddings? All right, so this is a very, very important slide here. because this concerns how we interpret sentences or text chunks for RAG or for retrieval augmented generations. We typically assign a score for each text chunk, and then we do cosine similarity to retrieve out the relevant passages. And how is this trained? We don't have the latest model by OpenAI, the text embedding 3 large and small, but we do have the text ADA 002 version. And this version, they released a paper for it. So thank goodness for open source. Unfortunately, they didn't have a paper for the latest one. But in the earlier paper, we analyze how this is done. Okay, the idea is this. They also use this thing called unsupervised learning. Oh, actually, no, they use contrastive learning. But the idea of contrastive learning is also on a unlabeled data set. Okay, because the data set, what they use is this. They use a very naive rule to scrape the entire internet's data. Neighboring sentences that appear next to each other are considered similar. Sentences that are not next to each other are not similar. So this is a very naive rule, but this allows us to do this thing, unsupervised learning again, where we just take the world's data and then we can just group together by sentences, and then you have your training set already. Next door sentences are similar, not next door is not similar. Okay, there's some problems with this. Okay, so I mean, I'm just going to highlight something. I don't want to harp too much on this, but like, for example, if let's say like Peter is a boy, and like maybe the next sentence is like Mary is a girl, then the next sentence is like Justin is a boy or something like that. So if you could do something like that, you will realize that in the same sentence or same paragraph, these two could be grouped together as similar. And then this other two could be grouped together as dissimilar. Can you see that there's a problem with this? Because actually all of the texts are all similar. Yeah. So, but the hope is that once you average out across the entire world's data, hopefully the embedding similarity could cancel out. Like that means there will be more of this kind of similar stuff to the dissimilar stuff, and you will learn the embeddings that Peter is a boy, Mary is a girl are more similar together. And there's some problems with the embeddings also. Like for example, it's like Peter is a boy, Peter is not a boy. Okay, they actually don't really do the negation that well using this method, because when you do negation in a sentence, in the paragraph level, sometimes maybe it's not a boy, then the next sentence is Mary is a girl. It could be in the same paragraph. All right, and whether or not it's a negation or not, it doesn't really make a difference. It's still considered as similar. So there are some issues with this because it's a very naive approach, but this approach enables you to do some form of unsupervised learning. Okay, over here is contrastive learning, because rather than doing next sentence prediction, we do whether is it similar or not. So the label is predict whether two sentences are similar or not similar. So this is the cosine similarity loss function here that tries to predict whether or not two sentences are similar. All right. This is very different from next token prediction. So the question I have for you is, why didn't OpenAI do next sentence prediction? Why do we not predict the entire next sentence? Okay, so I'd like to tickle your minds a bit. Why did OpenAI use this contrastive learning to do similar, dissimilar? Why not just predict entirely the next sentence? So like, for example, Peter is a boy. Why not I just predict entirely Mary is a girl? Any comments or any thoughts on this? Why can't we do next sentence prediction directly?
It seems like there's not enough context.
Okay.
One sentence to the next is often a different topic, or maybe a new paragraph, but it just doesn't feel like there's enough context to work with.
So that's a great response. So there's too many possibilities. So the answer is actually too many possibilities for next sentences. Too many possibilities for your next sentence. Okay, this is humongous. Okay, this means that if you want to predict stuff like Mary is a girl, if each token, let's say for example, one token is 100,000 possibilities. If your sentence has 10 tokens, can you imagine how many possibilities there are? That's the number of possibilities for this is 100,000 to the power of 10. Okay, that's like, okay, me just shift this somewhere. That is huge. If you were to do this, it means that there's a lot of things that you need to predict, and it's not possible for a probability-based prediction model to predict a very infinitely small probability like that. Well, yeah, it doesn't work that way. So unfortunately, doing the naive next sentence prediction is not going to be possible. Okay, so this is actually the same problem with images. All right, there's just too many pixels to predict, too many objects to predict, too many positions to predict, too many. Okay, but what we can do is some naive rule that says that, you know, next door sentences are similar, not next door is not similar, and then you try to just predict only similar or not similar. So it's either a 0 or 1. Okay, in this case, cosine similarity is basically it is actually -1 or 1. Okay, because the angle that is similar, if you think of it, the angle is so if we do the cosine similarity loss, the loss function should be -1 is not similar and 1 is similar. So it depends on your loss function you use. Okay, if you convert it to like 0, 1, then 0 will be not similar and 1 will be similar. So the thing that I want to highlight is that this learning is not the best. All right, that is why when you do retrieval augmented generation with embeddings, the embeddings are quite bad. I mean, they're not the greatest, because this is how it's trained. It's trained using contrastive learning. Okay, it's not the native unsupervised learning that the transformers have. So contrastive learning, again, not good. Okay, this is not great. Okay, I also don't really like contrastive learning. If you take a look at how contrastive learning is done, for every positive sample, you also need negative samples. And you know, if you train positive and negative samples like that, it doesn't scale that well. Like if let's say you have 100,000 examples, you know, then you need to have like for each positive pair, you could have like maybe 999 negative pairs. There's too many negative pairs compared to positive pairs, you know. And if in a high dimensional structure, it doesn't learn the high dimension structure that well, because instead of like doing like continuous vector prediction and so on, you know, you are trying to predict a binary token. Yeah, so you don't get much learning signal here. So how I put it? Okay, let me just erase everything. Let me tell you the problem with contrastive learning. So let's say you have 10 boxes here, and then you want to learn which boxes are similar or not similar. Okay, I don't know whether I drew 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's say you have 10 boxes and you want to find out which boxes are similar or not similar. So what would happen is like this. You have this box number 1. Let's say box number 1 is similar to box number 9. So, okay, this is an interactive segment, okay? How do I tell if box 1 is the same as box 9, okay? So, at each turn, you can choose 2 boxes. And I will tell you whether it is similar or not. Okay, let's play this game, all right? So, we have 2 boxes, box 1 and box 9 maybe are similar. Okay, so how would you play this game? Okay, anyone? Like, let's say I don't even tell you box 1 and box 9. I just tell you there are 2 boxes here that are similar. Okay, there are only 2 boxes in this group of 10 boxes. Okay, 2 boxes in 10 boxes are similar. How would you choose your two comparison pairs? Okay, in order to find out which boxes are similar. Anyone can tell me like a strategy you would use to find out which 2 are similar?
Maybe split the difference, you know, one in the middle, one at the one end, one at each end, and bring them in, see how you go.
All right, so you want to do like however way you do it, but actually the idea is, if let's say there's only 2 boxes that are similar, you kind of need to compare.
More or less all of them, yeah.
Yeah, all possibilities. There's no way to do it. So let's say you have 10 boxes, you need to do 10 choose 2, which is astoundingly huge number with 55 possibilities, and that's just 10 boxes. Imagine if you have 1,000,000 boxes, million choose 2. Good luck. Yeah, your number of possibilities you need to compare to learn that these 2 boxes are similar is exponentially large, and that's why contrastive learning won't scale. Okay, anyone who uses contrastive learning can only do that for small data, and also very narrow and restricted data. You want to do that for the world's data, you need next token prediction, you need unsupervised learning. Okay, so the way this sentence level embedding is trained, okay, it's not the best. Okay, it's not the best because it's not using unsupervised learning directly. It's using unsupervised learning in some sense. I mean, by just saying that, okay, neighboring sentences are similar, not neighboring are not similar. So you can get, without human labels, you can have a huge data set. Okay, but with that huge data set, because of the way it's doing, like saying these two sentences similar, these two are not, this is not exactly a great way to learn. I mean, this is actually very similar to the next sentence prediction, or they call it NSP in BERTs. In next sentence prediction is either 0 if it's not the next sentence, or 1 if it's the next sentence. So because of this binary signal, and like it's sort of like a contrastive learning kind of objective, it takes a lot of examples just to learn like maybe these two boxes are similar. When you could do that easily if you just do next token prediction, you just need 2-3 sentences, you can already learn that these two are similar. Okay, so this is one of the key reasons why embeddings don't work so well. And it's a difficult problem, okay, because the way that we train the transformer embeddings is not meant to represent the whole sentence. Okay, let me show you. When we train the transformer embeddings here, this embedding over here, so this is a food for thought. Does it represent the whole sentence? Think about it. Does it represent the whole sentence? What is the training objective for transformer? The training objective for a transformer is to predict the next token. So what we want to do is we just want to predict this next token. Does predicting the next token equals to having this embedding here being encompassing the entire meaning of the sentence? Anyone can tell me, like, or you just guess, do you think this embedding here necessarily represents every single thing at the start? Anyone?
No, you can use the same word in many different sentences. So if the word you output is bank, as we talked earlier, then it doesn't represent the rest of the sentence at all.
Correct. So actually, based on what it needs to do, it might actually choose to focus on other things. So for example, the cat in the hat too. Okay, this too doesn't really make sense, but it might just focus on in the hat because of attention. You might only focus on similar embeddings more. You don't have the entire sentence embeddings embedded into one token embedding. You don't have that. So this is one of the issues of trying to use transformers to do sentence level embeddings. Okay. The objective is not to embed the sentence in the transformer. The objective is just to predict the next token. So there's a mismatch in objective here. If we truly want to do a sentence level objective, okay, it's not possible because there's just too many tokens to predict for the entire sentence. Okay. However, I mean, I'm thinking of this like the last time I did this on the OpenAI, the embeddings. I had a similar there's one session I did. So I also was thinking of this idea where you can just do like this is your sentence, and like maybe the cat set on the map. So maybe is there a way to force it such that it can predict the meaning of the whole sentence? So maybe you could just put like repeat the sentence. So maybe if you add in this line, okay, this is my naive guess, all right? So maybe if you have this prompt, repeat the sentence, this next token here, could sort of pay attention to the entire sentence already. I don't know, maybe it just pays attention to the word the, because, yeah, but the idea that you can ask it to try to repeat the sentence, and then you take the token embedding here at the last part, take this token embedding, okay, may be prompted to look at whole sentence. So, maybe it could get the meaning of the sentence. Yeah, I mean, this is just my very naive way of thinking. I haven't tried it out yet. But, perhaps we could nuance the token embedding such that it tries to look at the whole sentence rather than just, predict the next token by, making the objective for the next token prediction becoming the sentence objective. So just a food for thought. I just thought of this today. Yeah, but I do think that the way that is done using contrastive learning, at least in the learning text and code jointly paper, I don't think that's a great method. I think that the method is it can be flawed. Yeah, this method here is a bit, yeah, doesn't learn that well. Yeah. So how do they actually do this? Okay, how do they nudge the transformer embedding? Okay, because what they did is they start with the transformer pre-trained embedding. They nudge the transformer pre-trained embedding, which is, if you look at this diagram here, is this last token embedding here. What they did was to take this last token embedding and then nudge it closer to have the meaning of the whole sentence. And how do they do that? They do that using contrastive learning. So that's why I explained just now. They do that using contrastive learning, and they try to nudge the meaning of that last vector. So this is the vector for the last token after all the layers of attention. They try to take the last token embedding at final layer of transformer, okay, and nudge it towards a sentence level meaning. So by using contrastive learning, they try to group similar sentences together and these similar sentences away from each other. And from that, it is a great idea actually. The idea, because the transformer embeddings, they only could take the last token embedding. Okay, they only could take the last token. Okay, why? Okay, because of causal transformer. If you take any other token here, you don't have the last token. You cannot pay attention to tokens beyond you. So the only logical choice, if you want to use a transformer to do sentence level embedding, is to take this embedding here, which will theoretically be able to attend to every single token in front of you. Okay, so the idea is nice. We use the contextual learning abilities of transformer. We try to take out this token here. Okay, the learning method is not correct. The learning method is a bit inefficient using contrastive learning. So there's a limit to how much you can nudge this final embedding towards your desired meaning of the entire sentence. There's a limit to that. So I would say that, maybe, this is why the embeddings don't do so well. Yeah, but I haven't really thought of a way to nudge it better. Yeah, maybe I could try using what I said just now, like repeat the sentence, and then you try to take the embedding after that. Maybe the embedding will be closer to the meaning of the whole sentence. Yeah. Any thoughts? Like how can we nudge the meaning of the last layer embedding better to represent the sentence? Do you have any thoughts? Like my thought is just repeat the sentence and then yeah.
Yeah, I think you were close to the mark before when you said it gives. You're asking the wrong question. And I think this is optimized for that next token prediction, right? And next token wise, they're not that interested in the meaning of the sentence really. They just got to get the right guess for the next token. So my suggestion is you probably need a different. It doesn't feel like that's all about. Like a sentence is an important grammatical linguistic construct, right? All languages have some version of them that I'm aware of. Right? I'm no linguist, but it feels very specific to language, right? So we were talking earlier about the behavior of of images, right, in terms of encoding them and so on for learning systems. We're talking about position and relativity and blah, 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 but a sentence is more constructed, right? So there's meaning in there, but I don't know if I want to put a lot of emphasis around it, if that makes sense. So to get the meaning of a sentence is hard, because I don't think that's a thing that has been done really to date. That hasn't been the goal. The goal's been guess the next token.
Yes. Yeah. Actually, talking with you today, I have a new insight. So thanks so much for talking. Let me just explain what I just thought of. Predicting the next sentence is actually very similar to predicting images, like image patches, because there's so many things to predict. And there's a lot of things that you want to predict. Actually, you want to predict the emotion, you want to predict the context, you want to predict the person, maybe you want to predict action, just like images, one image can contain a lot of meaning in just those pixels. So maybe we are using the wrong like kind of objective to predict. Maybe what we should do is we could have embeddings for different kind of predictions. So actually this is quite linked to what I wanted to cover today, context-dependent embeddings, where you can actually map the embedding based on like a certain category. Like for example, you map based on emotion, then you know your meaning might be different. So like for example, like I have a sad, I had a happy day with my friends today. Yep. So if let's say this is the thing, then in terms of if you want to map this sentence to context, right? Emotion would be happy, context would be daily life, and then the person would be me and friends, and action is spending time with friends. So you can see that like, okay, I don't know whether this, where should I put this? Yeah, I don't know whether this kind of thing would be better. So instead of trying to predict naively the sentence itself, maybe we can split into certain categories that we want to predict, and we predict those categories instead. And yeah, the way we predict those categories could jolly well just be a next token prediction objective.
Yeah, I think you could, but I'm not sure. Personally, I'm not sure this is the right technique to do it. That's all.
Yeah. No, because I do think there's a lot to unpack if we want to predict the entire sentence. But you know, if let's say I predict part by part, which it could be done quite easily with like maybe ChatGPT can analyze the sentence and predict like each of this thing here. Maybe using strict JSON or something, you can predict each of these context categories one by one. And you know, I'm thinking that you know maybe we can use this to like you could reconstruct the next sentence with such abstraction spaces. Maybe instead of predicting the next sentence directly, we predict it indirectly by generating the next sentence using certain parameters.
Well, I think that's the thing at the moment is it implicitly gets the next sentence today by getting the next token and the one after that and so on.
So all
it
these
builds,
categories
it
actually
builds a
are
context
implicit.
as it goes, right?
They're implicit in the transformer model already. Yeah, that's why you can do the next sentence prediction. I mean, you can generate next sentences quite well. The problem is if we extract out everything into one embedding, then it won't be able to do that well.
No, and that's not its design, right?
Yeah. So I'm actually thinking, you know, rather than having an embedding to do everything in one, why not have embeddings that do different categories like emotion, context, person, action, and so on? Then you just compare the right category that you want. Then the embedding might be more tailored to the task than just having a single embedding for the whole sentence.
Yeah. And I think that's kind of there needs to be a more generalized solution, right? So one way is to do many specializations, right? The combination of experts, proper term for that. Another way is if you can find a generalized solution. But you know, we know from just from maths, an individual case is easy. Generalized solution is much harder.
Yeah, let me think more about this. I think this is a problem that no one has solved yet. Yeah, and this is an important problem actually, because if you try to use this sentence embeddings for retrieval augmented generation systems, you realize it doesn't work that well. So
It'll work. I think I was going to say quickly, it works for well-structured, well-written text. So I was considering playing with legislation, and that should be okay actually. Right? But at the same, where there's a consistent language and style and things like that, and it is actually carefully structured. But where you're looking at, say, and even at chat logs where it's highly unstructured, although it's actually question response is pretty much the structure. So the challenge, I think, is to do something where you have a generalized, where you can choose the nature of the abstraction you're looking for, or where you do the abstraction in such a way, it doesn't matter. You don't need to choose.
True. It would be best if we can learn the abstraction space. Like, in this embeddings here, all this could be an individual expression space of like living object, animal, royalty, and so on. This individual dimensions could be abstraction spaces already that are learned from the data directly. Yeah, so it'll be good if we could already come up with something like that. So I mean, in some sense, the embeddings already sort of capture that. It's just that because of next token prediction, it doesn't exactly capture like the meaning of the whole sentence, which is what we want in a sentence embedding. The next token prediction is not the right objective for sentence prediction. Yeah. So I think I get your point in the sense that this abstraction spaces is best if we don't hard code them. It's best if we can learn them directly because there's just a lot to code. Yeah. But I'm gonna try out something. So like after today, I'm gonna try out to do in the prompt, like whether or not just simply from the prompt, like simply from the prompt, like sentence is A, and then like maybe what you do is you summarize the sentence. Or you can just put like the key meaning in the sentence is, and then you just take this next token here. Maybe you can get the sentence meaning better because the next token objective, you align it with the sentence prediction objective. I'm thinking like that, whether, natively through the transformer architecture, whether the tokens could already align themselves to do the task better. Yeah, so and at least this is my thoughts. These are my thoughts after today. Yeah. Okay, yeah, so actually there's a lot of things to unpack. I don't think I can cover all today, so I will just skip to the discussion now. We'll cover the part on my research on how to do like embeddings with like this other stuff like shorter text for embeddings. All these things we'll cover next session. Okay, so context dependent embeddings as well. So let's just go straight to the questions to ponder. So now we return to what questions that we have just now, like how many dimensions should an embedding have? So like in the text ADA 002, that's about 1,500 plus embeddings. And then like the recent model, the text embedding tree large, that is about like 3,000 plus embeddings. So how many embeddings are good? Anyone like to? I mean, there's no answer to this actually. Yeah, if there's no fixed answer. Yeah. So
the least you can do well.
Yeah, that's a good answer. So that's true, because if you put like too many dimensions, maybe there's a lot of redundancy in the dimensions. And when you do cosine similarity, it's not that great to do with too many dimensions because like there's a lot of factors. If you can do well with 2 dimensions, you should just use 2 dimensions. I don't need to learn 6 dimensions or 7 dimensions. So I like this idea. So I would say that, I mean, based on my experimentation with like text embedding tree large, actually the extra dimensions help for complicated text. So the more complex your problem, the more dimensions you likely need to express all your data. So if let's say you don't need that many, then of course 1,005 would work better. Yeah. So this is not a question that can be solved. Okay, you just need to experiment and see what works well with your data. Okay, so next. Okay, this question here, I think we skip for the next one because this one, there's a slide I covered on like re-rankers where you put all of the things together into one, like here. Okay, but this one I think we'll cover this next time. All right. So the last question is, I think this we should cover today. Are there any limitations in the training process for embeddings? Okay, just now we talked about it. The main thing is contrastive learning is slow to learn. Next sentence, objective not really present in next token prediction. Any other issues that you all have to contribute to this? Like what are the limitations in the training process for like sentence embeddings? I think these 2 are the main ones. So before we end today, I just want to show you something. There's actually let me just go back to the slide. There's actually new embedding model by OpenAI. And you can see that in the text embedding ADA 002, you see that stuff like have, do not have, they are given quite a high similarity score. So similarity score of 1 means the most similar. Jonathan was present, was absent is given like a score of 0.94. Present, absent is like 0.82. Present, not present is 0.85. These are high values. Like above 0.7 is generally quite high for embeddings. So it means that it treats the negation and the non-negated sentence about the same, right? Which is an issue of like the next sentence, contrastive learning. I said, if let's say the sentence is negated, but is also associated with the same context in this paragraph, you will not care about the negation, right? Look at this text embedding tree large. Same phrases, but we get much lower similarity. In fact, very low. And this is amazing. They seem to have fixed the negation part. So this is the question that I have for everyone to ponder. How did they do it? Okay, because it's not released. They did not release their code. How did OpenAI solve the negation issue in embeddings? Yeah, before I offer my answer, you all have anything you want to add first? Okay, if not, I'll just...
I was just
yeah.
going to say, you can, these days, the systems, the LLMs know enough, it's easy to generate a corpus of negations. And you would use them as a, oh no, I was going to say contrastive, spit that word in my head now. But, you know, in order as a, to properly get the negation, they need to score it correctly and use that as a mechanism as generating the embeddings.
Yeah, so what I'm thinking is like this. What they could have done is they could have artificially created a training data set, like what you said. And this training data set, you assign a dissimilar score. So the label is always dissimilar. Then you can just like negate the original sentence. Yeah, so you could hard code this objective in by feeding it, like, you know, there are two sentences in the contrastive learning. You could just say that this, okay, maybe I go back to the slide again. This sentence and this sentence, you could generate the sentence like this is your original sentence. And then this is like maybe GPT-4 generated negate. So you could just say these two are not similar, all right? Or if you have the original plus generated similar, you could just say that this is a similar label. Yeah, so you could do a lot of artificial labeling like that. You don't have to crawl the internet for the data. You can just use what GPT-4 or one version of LLM, what he has learned from the web, ask it to generate another sentence and say similar or not similar. And you can generate your own data set. So that's a great thing. I think that's what they did actually. Maybe they didn't just do for negation. You can also do for, you know, like for like past tense, present tense, you know, whether like entity is present, you know. So it depends on how you want to define by similar or not similar. So this is the issue with this, you see. What is similar? What do you mean by similar?
Does the fact that that similarity appears to be assessed in very few dimensions, which may lose the value of having multi-dimensional embedding, is that in itself a weakness that could be addressed to find a better similarity measure that takes into account large numbers of dimensions?
Yeah, I think so. So as what I was alluding to earlier, like I think there needs to be different things. Like for example, you have a person, you have a context, you have action, and so on. So maybe all this could have their own embeddings. Like you could have like an embedding of like 0.1, 0.2, 0.3 for this. And all these are learned by maybe prompting it differently. So that this embedding represents the different dimensions of your sentence. So there's no one metric, you see. There's a lot of ways to measure similarity. So like in RAC, also like you want to say similar for category A, similar for category B, you know, there are two different similarity metrics. You cannot just use the same embedding for both. So you might need different embeddings for each of these labels here. And then you just choose the right labels in like this is what I call multiple abstraction spaces. And then you choose right abstraction space for your query key matching. So this is not done right now. I think we need to do this. If not, your rec will always fail. All right. This sentence embedding is so crude. Okay, you look at the objective for sentence level embedding, similar or not similar, it's just 1 or 0. Like it's 1, 0 or 1 minus 1. You know, it depends on how you what loss function you use over here. So it's a binary objective. And the binary objective for similar or not similar is like so crude. You don't have any different dimensions of similarity, you know, because similarity could be similar in this topic, similar in this other topic, and so on. So I do think we need to redo this learning of embeddings. We cannot just have one embedding for sentence. You should have multiple embeddings for sentences, so that based on what you need, okay, like even negation can be one of them. Like, yeah, you could actually draw the right embedding that you need in order to solve the comparison you need. Yeah, so but it's tough. It's tough because right now when you do rec, you just take the two embeddings, you just do a dot product. Very easy. If we were to do this approach, you will first need to find out which category you want to compare to, and then find the right embedding to compare. So it's one extra step, but I think it will help improve the accuracy a lot more. So yeah, Bill, is that similar to what you were thinking? Okay, so yeah, it's all right. So I think this is a good thing to end on, because exactly how you do this context-dependent embeddings is exactly the focus of my research in the next few slides. All right, and I also will do another set of research to just say that like this is a sentence A, and then like summarize the sentence or something like that. So I try to do something like this to see whether this embedding is actually better than just taking the embedding of the original sentence itself. So there are some interesting things that we can do to try to nudge the next token embedding closer to the sentence embedding. And also like the other one here is multiple sentence embeddings for different contexts. I think those are very viable paths to explore to improve the sentence embedding representation. Okay, if not, I would like to end here. Yeah. One last round. Any other final words before we end? All right, and yeah, thanks for coming, and I'll see you all again next time to talk more about the context dependent embeddings. Okay, thanks everyone. Bye.
Bye. Thank you.
Thanks.
Bye.